Morning students, today we are going to see the topic theory of space curves under the subject differential geometry. I am DR.G.SUDHA, Assistant Professor of Mathematics, A.D.M.COLLEGE for Women, Autonomous, Nagapattinam. So let us go for the definitions. Differential geometry is the study of properties of space curves and surfaces with the help of vector calculus. This geometry examines in more details the curves in space and surfaces. Whereas the differential geometry of the plane curves deals with the tangents, normals, curvature, asymptotes, involutes, evolutes, etc., which have analyzed for space curves. Next, let us go for the definition C infinity function and C power omega function, etc. When a function is infinitely differentiable, then f is said to be of class infinity, or function itself is called C infinity function. Next one is C power omega function. That is the function f is said to be analytic over I if f is single valued and f possesses continuous derivatives of all orders at every point of I. This class of functions is denoted by omega. Already you know the function that is symbol omega. The function itself is called C power omega function. These functions have power series representation in the neighborhood of every point of I. Next, let us go for the vector valued function R vector. You know well the value of R vector, already studied in the lower classes. That is R vector is already you know the xy z is the R vector. A vector valued function R equal to R of u defined on I is said to be of class M. It has a continuous mth order derivative at every point of I. If we represent R as R is equal to x, y, z, then the above definition implies that each of the components x, y, z of class M and x, y, z are functions of u. Next, let us go for R dot. What is mean by R dot? That is dr by du. Already you know well. If R dot is equal to dr by du, never vanishes on I, then the vector valued function R equal to R of u is said to be regular. This implies that x dot, y dot, z dot will never vanish on I simultaneously. A regular valued function R is equal to R of u of class M is called a path of class M. Two paths R1 and R2 of class C power M defined on I1 and I2 are said to be equivalent if there exists a strictly increasing function that is phi of class M which maps I1, I2 such that R1 is equal to R2 composite phi. This is equivalent. Next, let us go for the definition arc length. Arc length means let R is equal to R of u with the path with the parameter u belongs to I. As u varies over AB that contains in I, the path is an arc length of the original path joining A and B. That is the initial point and the terminal point. Let delta be the subdivision of AB as follows. Delta is equal to A is equal to U0 is less than U1, less than U2, etc. less than UN is equal to B. A is the initial point and B, U1 is A, that is equal to U0 is the initial one, and terminal point is UN is equal to B. Corresponding to this subdivision of delta of AB, let L of delta is equal to summation R of ui minus R of ui minus 1. Then L of delta gives the sum of the lengths of the sides of polygonals inscribed with the curve by joining the successive points on the path. Any addition of new points like ui dash in the side ui minus 1, ui, that is ui dash, increases L of delta, since modulus of R of ui minus R of ui minus 1 is less than or equal to modulus of that is, you can split the modulus into two modulus, that is R of ui dash minus R of ui minus 1 plus R of ui minus R of ui dash. You can add the R of ui and subtract R of ui, tally R of modulus of R of ui minus R of ui minus 1. That is no change. Since A is not equal to B, as delta varies overall, possible subdivisions of closed AB. We obtain a non-empty subset L of delta of real numbers. The least upper bound of the set L of delta be real numbers is defined to be the length of the arc between A and B. Next, let us go for theorem. That is R equal to R of u is the parametric representation of the curve where u belongs to AB. The length of the curve is equal to length means small s, length is denoted by the letter small s, is equal to s of u is equal to integral over a to b modulus r dot of u into du. Proof: for a subdivision delta is equal to a is equal to u0 less than u1 less than u2 etc. un is equal to b. The initial point is a and the terminal point is b. That is u naught is equal to a and un is equal to b. We have L of delta, already mentioned in the previous slides. Again repeat the same. L of delta is equal to summation modulus of r of ui minus r of ui minus 1. Since r is at least of class C dash, we have modulus of r of ui minus r of ui minus 1 is equal to modulus of integral over ui minus 1 to ui into r of u du. Using L of delta taken as equation 2 and the difference of the value r of ui minus r of ui minus 1 here taken as equation 3, take it as equation 3. Using 3 into, we obtain the value L of delta is equal to summation modulus of integral r dot of u into du. Summation integral over lower limit ui minus 1 and the upper limit is ui. By Swash inequality we have already you know very well about the Swash inequality, that is summation modulus of integral r dot of u du less than or equal to summation integral modulus r dot of u du. L of delta is less than or equal to, using the above, integral modulus r dot of u into du. So that we have L of delta is less than or equal to integral r dot of u is simply denoted as r dot. R dot of u is denoted by only r dot. So L of delta is less than or equal to integral modulus r dot into du. Since the right hand side of the above equation, that is equation 4, is finite and independent of delta, the set L of delta for all possible subdivisions delta of AB is a bounded set of a real number and it is bounded above. So the least upper bound of L of delta exists as a finite quantity. We shall show that this upper bound is actually a length of given arc. If S is equal to capital S of u denotes the arc length from A to u. Then S of u is equal to S of u naught gives the arc length between u naught and u. U naught is the smallest, that is A is equal to u naught and that is u is equal to b. Since we have defined as the arc length as the least upper bound of the arc length, which is the least upper bound of L of delta, we have from the previous one, equation 4, S of u minus S of u naught less than or equal to integral u naught to u modulus r dot of u into du. Since the length of the chord joining r of u and r of u naught is less than the actual length, we have modulus r of u minus r of u naught less than or equal to S of u minus S of u naught. That is equation 6. From 5 and 6 we get modulus r of u minus r of u naught divided by u minus u naught less than or equal to S of u minus S of u naught divided by u minus u naught, which is less than or equal to 1 by u minus u naught into integral modulus r dot of u into du, combining 5 and 6. That is equation 7. Next, taking the limit as u tends to u naught, we get from 7, equation 7 from the previous one. Limit u tends to u naught, take limit u tends to u naught in the 3 inequalities, we get limit u tends to u naught modulus r of u minus r of u naught divided by u minus u naught, which is less than or equal to limit u tends to u naught into S of u minus S of u naught by u minus u naught, that is less than or equal to limit 1 by u minus u naught into integral r dot of u modulus of r dot of u into du. Integral the u naught to u. Taking the limit as u tends to u naught, we get the result modulus r dot of u naught, binomial, that is modulus of r dot of u mean value theorem, which is less than or equal to the center value is denoted as s dot of u naught less than or equal to the last one is denoted by modulus of r dot of u naught. Hence s dot of u naught exists and has the value s dot of u naught is equal to, combining both value, here s dot of u naught lies between both r dot and r dot, so that we get the result equal. Hence s dot of u naught is equal to modulus r dot of u naught. That is equation 8. From 8 we conclude that s is a function of the same class as the curve, that is integral s dot of u into du is equal to integral s a to u modulus r dot of u into du. S dot, you know well, what is S dot? That is ds by du, isn't it? So integral a to u ds by du into du, that is equal to integral modulus r dot of u into d. S dot integral s dot du, we integrate that this, we get the value s. Limit, we are applying the limit lower limit a and upper limit u, that is equal to integral modulus r dot of u into du. Applying the limit upper and lower integral, we get the value s of u minus s of a, that is equal to integral modulus r dot of u into du. As s of a is equal to 0, small s equal to s of u, that is equal to integral modulus r dot of u into du. That is equation 9, where s denotes the length of the curve from a to u. Next, let us go for the definitions. Tangent and osculating plane. What is mean by tangent plane and osculating plane? First, let us go for the definition. Tangent vector at P. Let P and Q be the two neighboring points on gamma with the parameters u0 and u respectively. The parameters with P and Q are very close together in the sense that when Q tends to P, u minus u0 tends to 0. The unit vector along PQ tends to the unit vector at P as Q tends to P. This unit vector is denoted by T vector as defined to be the unit tangent vector at P. Next one is the tangent line. Tangent vector. The line through P parallel to T vector is called the tangent line to gamma at P. If R vector, capital R vector is the position vector of any point on this tangent line to gamma at P, then the vector PR vector is called the tangent vector to gamma at P. Next one is the definition, osculating plane. What is mean by osculating plane? Let gamma be a curve of class greater than or equal to 2. Gamma be a class of curve of class greater than or equal to 2. And let PQ be the two neighboring points. P and Q be the two neighboring points on gamma. Then the limiting position as Q tends to P, whenever Q tends to P of that plane which contains the tangent line at P, and the point Q is called the osculating plane of gamma at P. Next one is the point P on the curve for which gamma double dash is equal to 0 is called a point of inflection and the tangent line at P is called infleximal. Next one, let us go for to prove the theorem. If gamma be a curve of class m greater than or equal to 2 with arc length s small s as the parameter, if the point P on gamma as parameter 0, the equation of the osculating plane is, that is on box value of box of capital R vector minus small r vector of 0, comma r dash of 0, comma r double dash of 0 is equal to 0, where r vector is equal to 0. This is a very important theorem, this one. Proof. Using the arc length SS parameter, let 0 and SS the parameters of P and Q. Again repeat. Using the arc length SS parameter, let 0 and SS the parameters of P and Q. Let capital R vector, already you know well, capital R vector is what? Capital R vector be the position vector of point on the plane containing the tangent line and at P and passing through Q. Thus, if small r vector is also a position vector of P, then the vector R capital R minus small r vector of 0, comma r dash of 0, comma r double dash of s minus r of 0 are coplanar. What's the condition for coplanar? If A, B, A vector and B vector, C vector are coplanar, then the condition is box value of A vector, comma B vector, comma C vector is equal to 0. Isn't it? You know well. Here also we are applying the same concept. The R vector is the position vector of P, then the vector capital R minus small r of 0, R dash of 0, comma R double dash of s minus r of 0 are coplanar. The condition is box value of the three vectors equal to 0. That's the equation 1. Since the curve is of class m is greater than or equal to 2, we have by Taylor's theorem r dash of s equal to small r vector of 0 plus s into r dash of 0 plus s squared by 2 r triple dash of 0 plus order of s squared as s tends to 0. That is we are taking as equation 2. Using 2 in 1. We have a box value of r minus r dot of, that is capital R minus small r of 0, comma r dash of 0, comma s into r dash of 0 plus s squared by 2 factorial. We are using the equation 2, that is s into r dash of 0 plus s squared by 2 factorial, r triple dash of 0 plus order of s squared minus r vector of 0. That is using the result 2. It is equal to 0 as s tends to 0. Neglecting the terms of the higher orders, that is the higher powers, the above equation becomes, what's the value? Box value of capital R minus small r of 0, comma r dash of 0, comma s into r double dash of 0 plus s squared by 2 or double dash of 0. That is box value of these values is equal to 0. That again, simplifying this one, simplifying the above box value, we get modulus of box value of r minus capital R minus small r of 0, comma r dash of r double dash of 0, comma r of 0, comma s into r dash of 0 plus capital R minus r vector of 0, comma r dash of 0, comma s squared by 2 factorial r double dash of 0, that is equal to 0. Since r double dash cross r double dash, it is the cross product. Both are same vectors, the cross product of the same vectors is 0, you know well, and s is a scalar. Here also we are applying the same concept, cross product of the same vectors is equal to 0. The above becomes s squared by 2 box value of capital R minus small r of 0, r comma r dash comma r triple dash of 0 is equal to 0. That means s squared by 2 is equal to 0. We are crossing the value. S squared by 2 in the product, so s squared into 2 into 0 is 0, hence the box capital R minus small r of 0, comma r dash, comma r double dash of 0 is equal to 0, hence the proof. Next we are going to see the theorem, box value of r minus r, capital R minus small r, comma r dot, comma r double dot. The previous theorem is r dash, r triple dash, here a dot product, box value of capital R minus small r, comma r dot, comma r double dot is equal to 0. Here u is the parameter of the curve gamma, then the equation of the osculating plane at any point r, the position vector, that is small r equal to small r vector of u. We have to prove that the box value is 0. Proof, we have r dash vector is equal to dr by ds. You know well the formula. Dash d r dash means differentiate r with respect to s, that is dr vector by ds. Again we are taking multiply du and divided by du with dr by ds. So we get dr by du into du by ds is equal to r dot. R dot means dr by du in divided by r dot by s dot. S dot means ds by du. Here du by ds is given, so it is the reciprocal, so that we are taking r dot by s dot. Further, r triple dash is equal to d squared r by ds squared. D squared means d by ds of dr by dr vector by ds, so that d squared r by ds squared. That is again equal to, we are multiplying du and divided by du in d by d squared r by ds squared, so that d by du into r by r vector by s dot du by ds, so that we are differentiating the above one, we get s dot into r double dot minus r dot into s double dot divided by s dot squared into 1 by s dot. Using these values of r dash and r triple dash in box value of capital R minus small r vector of 0, comma r double dash of 0, comma r triple dash of 0 is equal to 0. So that we get the value r double dash vector equal to r dot vector divided by s dot, and r triple dash vector is equal to s dot into r triple dot minus r dot into s double dot divided by s dot squared into 1 by s, which implies box value of capital R minus small r, comma r dot vector divided by s dot vector into s dot into r triple dot minus r dot into s double dot divided by s dot squared into 1 by s dot is equal to 0. That is box value of, we are simplifying the above step, we get box value of capital R minus small r, comma r dot vector by s dot into r triple dot divided by s dot squared minus r dot s double dot divided by s dot cube, which is equal to 0. We simplifying this step, we get the value, box value of difference of these two values. That is box value of capital R minus small r, comma r dot by s dot dash into r triple dot by s dot squared minus box value of capital R vector minus small r vector, comma r dot divided by s dot into comma r double dot divided by s dot cube is equal to 0, since r dot vector cross r dot vector is equal to 0 and s dot is a scalar. Already you know same cross product of same vectors is equal to 0. We are using the same result here, so that the above becomes box value of r capital R minus small r, comma r dot by s dot, comma r dot by into s double dot divided by s dot cube is equal to 0. From this step we get box value of capital R minus small r, comma r dot vector by s dot, comma r double dot triple dot divided by s dot squared is equal to 0. And we get simplify again this one, s dot squared is going to 0, that is box value of capital R minus small r, comma r dot, comma r triple dot is equal to 0, which is the equation of the osculating plane. Next one is the example. Find the equation of the osculating plane at point u of the circular helix. R vector equal to a cos u, a sin u, b u. A cos u we are taken as x. R vector is already you know well, R vector is equal to denoted by x, y, z. Here x value is a cos u, y value is a sin u and z value is b u. Given that R vector equal to a cos u, a sin u, b u. Here x equal to a cos u, y is equal to a sin u and z equal to b u. General equation of the osculating plane is determinant of capital X minus small x, y capital Y minus small y and capital Z minus small z, x dot y dot z dot x double dot y double dot z double dot is equal to 0. We are applying the x minus small x, small y, small z, a cos u, small x, a sin u is the small y value and small z equal to b u. X dot a minus a sin u, y dot equal to a cos u, z dot equal to b, and x double dot is minus a cos u, y double dot is a sin u, z double dot is equal to 0. We are applying the modulus value, we get equal to 0. We expand the determinant value. We expand the determinant value in row wise. X minus a cos u into 0 plus a b sin u minus y minus a sin u into a b cos u plus z minus b u into a squared sin squared u plus a squared cos squared is equal to 0. Again we simplifying the steps, we get ab capital X sin u minus a squared b sin u cos u minus y into a b cos u plus a squared b sin u cos u plus z a squared minus a squared bu equal to 0. We are simplifying this one, abx sin u minus yab cos u plus z a squared minus a squared bu equal to 0. Minus a squared b sin u cos u plus a squared b sin u cos u get cancelled. Dividing a on both sides, we get bx sin u because a is common for all the terms, so that we are dividing a on both the sides. So we get bx into sin u minus yb into cos u plus za minus ab u is equal to 0. We are taking b, take it out because b is common for 3 terms, so that b take it out. So b into x sin u minus y cos u minus a into u plus za is equal to 0. Next let us go for the definitions, principal normal and binormal. Already we have studied osculating plane and tangent plane. Next we are going to see the topic principal normal and binormal. What is mean by normal plane and principal normal and binormal? First one is the normal plane. Okay, let P be a point on the curve gamma. The plane through P orthogonal to the tangent at P is called the normal plane at P. Again repeat. Let P be a point on the curve gamma. The plane through P orthogonal to the tangent at P is called the normal plane at P. Next one is the principal normal. The line of intersection of the normal plane and the osculating plane is called the principal normal at P. The unit vector along the principal normal is denoted by n vector. Again repeat, the line of intersection of the normal plane and the osculating plane is called principal normal at P. The unit vector along the principal normal is denoted by the letter n vector, small n vector. Definition: binormal. What's mean by binormal? The normal at P orthogonal to the osculating plane is called the binormal. What is binormal? The normal at P orthogonal to the osculating plane is called the binormal at P. The unit vector along the principal normal is denoted by small b vector. Orthogonal, that is principal normal value denoted by the vector b vector, small b vector. The next one is rectifying plane. The plane containing the tangent and binormal is called the rectifying plane. Thank you.